So today we get to the fundamental theorem of calculus, which has always kind of made me smile for a couple of reasons. Number one is you're like, how is it that we've gotten almost halfway through the year and we're just now learning something that is fundamental? Well, the fundamental part of it is not that it's the most basic part, but the fundamental part of this is that historically, calculus was actually developed as two different things. Integral calculus and derivative calculus were developed sort of separately, and no one really understood that they're actually related to one another, right? And so the fundamental part about it is that the fundamental theorem relates how derivatives and integrals are related to one another. Okay? The other part of it that makes me smile is that it's called the fundamental theorem of calculus, but there's two different parts to it. Some books call it the first fundamental theorem and the second fundamental theorem. I've always thought it was kind of dumb. I'm like, well, it's two completely separate things. Why not call it something else? But this is what happens when they don't invite me to the meetings where they decide how to, name things. So here is what your book calls part one of the fundamental theorem of calculus. And it says that if f is continuous on the closed interval from a to b, and by the way, paying attention to that part, frequently if you're asked to justify something is true, then you must appeal to the requirements of the theorem. You must say that it meets those minimum requirements. It's got to be continuous. That's the only requirement on this one. Then the function capital F of x, which is the integral from a to x of f of t dt, is differentiable on the closed interval from a to b. And the derivative of capital F with respect to x is the derivative with respect to x of the integral from a to x of f of t dt, which is f of x. So at its most basic, it's overstating it a little bit, but at its most basic, the derivative of an integral defined function simply is the function at x. So because when we're, in a little while, we'll do the second part, when we are evaluating this, we're going to find an antiderivative. And if you take the derivative of an antiderivative, you end up back where you started. Okay, so I'm going to show you a couple of very basic ones, and then we're going to look at some of the, oh, well, that's not quite the same. So, for example, this one. We want to take the derivative with respect to x. So notice that in the integrand and the variable of integration is t, but one of my limits of integration is x. So this is a function of x. So I'm taking the derivative with respect to x of this. It does not matter what the lower limit is or what constant it is. Now, if it's not a constant, that's something different. But this can be any constant. It does not matter at all. As long as this is simply x, which in this case it is, this is just going to be cosine of x. Done. And again, the way you want to think about it is that the integral is going to find an antiderivative, and this is doing a derivative. They undo one another. After we do the other part of the fundamental theorem, I'll come back to this one and show you that you can use the other part of the fundamental theorem to do this. All right, so here, same thing. The derivative with respect to x of the integral from 0 to x, as long as this is a constant on the lower limit, we're good to go. This is just 1 over 1 plus x squared, and that's it. Now, of course, it's calculus, so it can't be just that simple. So here, we're doing the derivative with respect to x of the integral from 1, not to x, but to x squared. So when I'm taking the derivative, because this is not just x, I have to apply the chain rule. So this is going to be the sine of x squared times the derivative of x squared, which is 2x. So this is 2x sine of x squared. All right, how is the next one different than the previous ones have been? Yeah, x is the lower limit. But when we looked at the properties of properties of integrals, I can switch those two as long as I multiply by -1, right? So I can rewrite this as the derivative with respect to x of the opposite of the integral from 7 to x of 4t cosine t dt. So now it's just like the first two were. I'm going from a constant to x. So this is going to be -4x cosine x. And then this last one, I'm going to show you why it works, and then we're going to talk about how to do this a lot faster. Okay? So notice here, both my lower and upper limits of integration are in terms of x, right? You're like, I don't really like that. Okay. So I'm going to rewrite this as the derivative with respect to x of the integral from 3x to, it does not matter, pick a constant, any constant. All right, 1. 1 over 2 plus e to the t dt plus the derivative with respect to x of the integral from 1 to x to the 4th of 1 over 2 plus e to the t dt. That makes sense? That's again one of those properties of a definite integral. Then I'm going to do 2 steps. I'm going to switch the order because I'm going to switch the limits of integration here so that I get a negative. And I like having the negative in the middle instead of at the front. So we'll have the derivative with respect to x of the integral from 1 to x to the 4th of 1 over 2 plus e to the t dt minus the derivative with respect to x of the integral from 1 to 3x of 1 over 2 plus e to the t dt. So now applying the fundamental theorem and applying the chain rule to both of these, because neither of them it's just x, we'll have 1 over 2 plus e to the x to the fourth times 4x cubed minus 1 over 2 plus e to the 3x times, because of the chain rule, 3. Now, in practice, there's absolutely no need to go through all of those steps. Because notice what I have here at the front is what I would have if this was a constant, right? Minus this part here where the 3x, if this had been a constant, it would have been minus this. So there's no need to go through all of those steps. You can just straight to the answer on these. Okay, and then this is the second part of the fundamental theorem, which says that if f is continuous on the closed interval from a to b, again, just continuity is all you need, and if capital F is any antiderivative of little f on the closed interval from a to b, then the integral from a to b of f of x dx is capital F of b minus capital F at a, which makes sense if you think about it this way. The other way to think about it is if I have the integral from a to b of f prime of x dx, that's going to give me the change in f. This is sometimes called the evaluation part of the fundamental theorem. We'll look at some examples at just a second, but let's back up for just a moment to this up here, okay? So if I was to actually do the evaluation part, don't worry about writing this down, it's going to be messy and everything, but I'd have the derivative with respect to x of, by the second part of the fundamental theorem, what is an antiderivative of cosine? Sine. So this would be the derivative with respect to x of sine of x minus the sine of negative pi, right? And then when I take the derivative with respect to x, the derivative of sine is cosine of x. And the derivative of this, which is a constant, and it doesn't matter if you don't remember your unit circle well enough to remember that it's 0 anyway, but that's going to be 0. The fundamental theorem, part 1, just lets you get there a lot quicker. It's also helpful for things like this one, where I don't know an antiderivative for the integral of 4t cosine t dt. I don't know what the antiderivative of that is, because it's a product, and I'm like, okay, how did I end up with that? It's not 2t squared sine t, because if I'm taking the derivative of 2t squared sine t, I have to use the product rule, and I'm going to get two different things, right? I'm going to have two terms. This just has one term. The fundamental theorem lets you go, I don't care that I don't know the antiderivative for this. The derivative of this integral defined function is just this integrand at x. So that's actually the power of the first part of the fundamental theorem. All right, so let's try this. Evaluate the integral from -1 to 3 of x cubed plus 1 dx without a calculator. Up until now, we've always used a calculator for this. So first, I want to find an antiderivative for x cubed plus 1. What can I take the derivative of that would give me x cubed plus 1? Almost. What's the problem with that? If I take the derivative of x to the fourth, what do I get? I get 4x cubed. Okay. I don't want the 4, do I? Yeah, stick a 1/4 out there in front. We'll actually learn that rule, but this is the power rule for antiderivatives. What you do is add 1 to the power and multiply by the reciprocal of the new power to take the antiderivative. Now, I want to evaluate this at 3 and at -1 and subtract. And the way that we'll typically write that is, you know how I've written like an evaluation bar like this before where I said, evaluated at x is whatever? Here we're going to evaluate it from -1 to 3. And that's the way that we typically write that. So you find the antiderivative and remind yourself, I'm going to evaluate that at 3 and at -1 and take the difference. So this is 1/4 of 3 to the 4th, which is 81, plus 3, minus -1 to the 4th is 1 times a 4th is 1/4, plus -1. So this is 81/4, and you're like, why don't you make that a mixed number? Well, you'll see in just a second. Plus 3 minus a 4th plus 1. 81/4 minus 1/4 is 80/4, which is 20. So this comes out to be 24. All right. So one of the things that we used a definite integral for is being able to find the area under a curve. So find the area of the region between the curve y equals 4 minus x squared on the interval from -1 to 3 and the x-axis. For these, I pretty much always sketch just a quick and dirty, all right, so what does this kind of look like? 4 minus x squared looks like this. And I know that it's going to touch the x-axis or intersect the x-axis at -2 and 2. So if I'm starting at -1, that's here. And if I'm going over here to 3, this is where it gets weird. It's like, okay, eventually these two are going to cross each other, right? So if I'm trying to find this area, if I just did the integral from -1 to 3, it would count this part as positive and this part as negative. But the question asked me to find this area. So that means I need to find this area and then add them together. So this is going to be the integral from -1 to 2 for the part that's above the axis of 4 minus x squared dx. And then if I do the integral from 2 to 3, this is going to return a negative, right? Because it's all below the x-axis. So I'm just going to do minus the integral from 2 to 3 of 4 minus x squared dx. So I need to find an antiderivative. An antiderivative of 4 minus x squared. What would that be? Minus what?
4x minus 1 half x to the third.
But if you did the derivative of 1 half x to the third, you'd get 3 halves x squared.
1/3.
Yeah. We want 1/3 x cubed. From negative 1 to 2. You can also write it with square brackets like this. It means the same thing. Minus, it's the same antiderivative here, 4x minus 1/3 x cubed from 2 to 3. So at 2, this will be 8 minus 8/3 minus at negative 1, that'll be negative 4 plus 1/3 minus at 3, this will be 12 minus 9 minus at 2, well, we already figured that. That's 8 minus 8/3. Be really careful with your signs on this. Notice here I've got minus this negative. It's real easy to forget that. Okay? So I'm just going to simplify without adding anything together yet. 8 minus 8/3 plus 4 minus 1/3 minus, I'm going to go ahead and add those two together, minus 3 plus 8 minus 8/3. So then the whole numbers, I've got 8, 8 is 16, plus 4 is 20, minus 3 is 17. And I've got minus 8/3, minus another 8/3 is minus 16/3, minus 1/3, that's minus 17/3. So it's 17 minus what, 5 2/3? So that's 11 1/3. One of the nice things about this, at least in terms of when you're doing this for homework and stuff, in addition to being able to check it in the back of the book if it's an odd, is that you can actually check this on your calculator. Right? You can, this is always dangerous because, maybe I screwed it up, but clear all this junk away. Do math 9, the integral from negative 1 to 2 of 4 minus x squared dx minus the integral from 2 to 3 of 4 minus x squared with respect to x. It's much faster than we were, but you get the idea. If this were a calculator active problem, you could shorten this also by doing the integral from -2 to 3 of the absolute value of 4 minus x squared dx. Because what that would do is that would flip all this part here that's below the y-axis back up to above the y-axis, and it's all positive now, and you don't have to worry about finding where it changes from positive to negative. And you can do that on your calculator also. Okay? For my money at least, when you're doing that on the calculator, so this is the integral from -1 to 3. The absolute value, I have trouble remembering where it's hidden. It's one of the things I don't like about the TI calculators is everything is there. Well, most things are there, but things are frequently hidden. So what I do is go second 0, which gets you to the catalog, and the absolute value is the first thing that's there. I'm sure it's in some math menu someplace, but I don't always remember where it is. And that'll give you the 11 1/3 quickly and easily. Okay? All right, let's do one more. Find the area between the curve y equals x cosine 2x and the x-axis over the interval from -2 to 4. And it says that you can use a calculator for that. Okay, you don't have to do a whole lot of work to do this. This is simply going to be the integral from -2 to 4 of, as we did in the last one, the absolute value of x times cosine 2x dx. So the integral from -2 to 4 of the absolute value of x cosine 2x with respect to x. And it is thinking hard about this one. La 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 la. There we go. 6.332. It always makes me nervous when the calculator does that, because sometimes it does that because you put in something that's actually impossible, but it's trying to do it, and it'll eventually just crap out on you. Now, if you were not using absolute values on this, what you would have to do is you would have to graph it x cosine 2x and I want my window to go from -2 to 4. And I really don't know how big or how small that's going to go. I'll go -5 to 5. That may not be big enough, but that's okay. Oh, what a pain this would be, because you'd have to do this part minus this part, plus this part, minus this part, plus this part, minus this little piece over here. You can see that the absolute value makes it a lot better. The other thing that makes this particular one better is this. Notice that, hang on a second so I can draw on this thing. Erase all of whatever the heck that is. If I go from -2 to 2, that this region and this region are exactly the same. And this region and this region are exactly the same. So I could use that symmetry and double the area between 0 and 2 and then just do this part. But even so, it's a pain because there's so many parts that are positive and so many parts that are negative. When I ask you to do it by hand, there's almost never more than 3 parts, right? There'll be, part above, part below, another part above at the worst. Okay? All right.